Hello, great friends. IBM is here with an episode of Learning Physics. Today, I decided to record February-March 2023 paper 2 or paper 2-2. This is strictly AS, and I hope you learned something from this question paper. For those of you who are sitting for your AS this coming May, June. This paper should be just acting as a guide to what you should expect in your May, June series. The question paper has been attached in the video description. There is a link to the in the video description which shows or which will take you to the question paper. You can download it, you can print it, and you can go through it as you watch the videos. The question paper is in the video description. You just copy the link, paste it in your browser, and the paper will open automatically for download. So without wasting time, let's go to paper February-March. This is February-March 2023, paper 2-2. It is supposed to be 1 hour and 15 minutes. I don't know how long I will take because I may try to explain more concepts in details, but it's supposed to be 1 hour and 15 minutes. I have no access to the marking guides for now, but I know I'm going to be a little bit more accurate and precise to the answers. Okay. So candidate name, my name is IBM. I'm attempting this question. IBM, that is my name. Ivan Brian Mulumba, that is my name. So this is paper 2 AS, level structured questions. You answer on the question paper. No additional materials are needed. Answer all questions. Use a black or dark blue pen. You may use an HB pencil for any diagrams. I know many of you make a mistake and draw with the pens. And when you want to rub, it becomes a challenge. Write your name, center number, and candidate number in the boxes at the top of the page. Write your answer to each question in the space provided. Avoid that business of drawing arrows for the examiner that the answer is on page 2. Do not use an erasable pen or correction fluid. Do not write on any barcodes. You may use a calculator. You should show all your working and use appropriate units. Information. The total mark for this paper is 60. The number of marks for each question or part question is shown in the brackets. So that is entirely not something very important. The document has 20 pages. Any blank pages are indicated. Some of the data you always have on your question papers, I think, has remained the same. G, C, elementary charge, 1U is equal to that, mass of a proton, mass of an electron, Avogadro's constant, the molar gas constant, Boltzmann's constant, gravitational constant, permittivity of free space. This time they have even given you this because many times candidates prefer to use this as a shortcut instead of using this. So you notice that this time they have given you 1/4 pi epsilon naught. So you can even use it in calculation. But of course, this will be in paper 4. It is not, you don't expect this in paper 2. Planck's constant, mostly in paper 4. Boltzmann's constant, mostly in paper 4. Some of the formula you may need from kinematics, you have S is equal to UT plus a half AT squared. V squared equals to U squared plus 2AS. Hydrostatic pressure, that is pressure due to fluids. Pressure due to fluids, that is density times G times change in height. Then upthrust is density times G times V, where V is entirely going to be volume, which is going to also be density times G times cross-sectional area times L. Then Doppler effect for sound, that one is F naught is equal to Fs, which is frequency of the source. V is the speed of sound, and Vs is going to be the speed of the source. Electric current, this time they have even given us electric current as ANVQ. Resistors in series, we sum them. Resistors in parallel, we get the reciprocals. Okay, blank page 3 is blank. Now we have started. Number 1. Underline all the SI base units in the following list. SI base units. They are said to be SI because other units can be expressed in terms of them. Just to give you a clue, there are 7 SI base units. We have kilogram for mass, seconds for time, We have temperature is Kelvin. We have amount of substance is mole. We have luminous intensity is the candela. We have current is the ampere. And these are 1, 2, 3, 4, 5, 6. Which one is missing? Mass. This is for mass. This is for time. This is for absolute temperature. This is for amount of substance. This is luminous intensity. This is electric current. So those are 6. Which one is missing? Which one is missing? Okay, length, which is in meters. Length, which is in meters. So we just look at the list. We have been given the ampere, which is SI base units. The column is not. Current is a quantity. Kelvin is SI base units of absolute temperature. So we have only 2. So of course, this is paper 2. You don't need to cross out others. The question just says underline. It is, although you may not be penalized for circling, but the question is saying underline. So it would be better if you underline. Okay. A toy car moves in a horizontal straight line. The displacement s of the car is given by the equation s is equal to v squared over 2a. This is a repeated equation. If you have watched my videos under kinematics, you will notice that this question has been repeated. State 2 conditions that apply to the motion of the car in order for the above equation to be valid. And in the past papers, questions that we discussed under kinematics, we said number 1, this equation is coming from s is equal to ut plus a half at squared. S is equal to ut plus a half at squared. This part is missing, meaning that the initial speed was 0. So 1, initial speed or initial velocity or initial speed is 0. Number 2, these equations of motion only apply to uniformly accelerated motion. Therefore, the acceleration must be constant or uniform. So acceleration is constant. The acceleration is constant, or you can say is uniform. I think I should reduce the size of this pen. An experiment is performed to determine the acceleration of the car in B. The following measurements are obtained. S is equal to 3.89 meters plus or minus 0.5%. V is 2.75 meters per second plus or minus 0.8%. Capture the acceleration of the car. So they gave us the formula above there as S is equal to V squared divided by 2A. S is V squared divided by 2A. So let's find the acceleration. I will just substitute quantities here. The quantities are in their SI units. So you notice that the acceleration S is 3.89 being equal to V squared, which is 2.75, and it is squared divided by 2 times the acceleration. I'll just press my calculator. The acceleration is going to be, if I make A the subject, the acceleration is going to be 2.75 squared divided by 2 times 3.89. So 2.75 squared divided by open brackets 2 times 3.89. So this is giving us 0.97. So this is 0.97. I'll just write here 0.97 meters per second. Determine the percentage uncertainty to 2 significant figures in A. So I make A the subject in this expression. They told us that S is equal to V squared divided by 2A. So if I make A the subject, it means A is equal to V squared divided by 2S. Okay, they gave us percentages, so here I will not waste any time. Remember, if I check if I have power and division, I deal with either fraction uncertainties or percentage uncertainties. So I would say the fraction uncertainty in A, which is absolute in A over A, is going to be twice the fraction in V, which is absolute in V over V, plus, we ignore this coefficient here, so I'll say plus um, absolute in S divided by S. If I multiply both sides by 100 or everything by 100, so this side by 100 times 100, it will be percentage. The other side times 100, it is also percentage. Therefore, I will say percentage in A is equal to 2 times percentage in V plus percentage in S, everything times 100. So percentage in V, since they gave us percentages, percentage in V is given as 0.8. So I'll say this will be 2 times 0.8 plus percentage in S is given as 0.5. So this is plus 0.5. Note that this coefficient 2 has been ignored when I'm dealing with either fraction or percentage uncertainties. The 2 you are seeing on velocity here was explained in errors and uncertainties. The power is multiplied by the fractional or the percentage uncertainty. So from my calculator, I'll have 2 times 0.8 plus 0.5. So this gives me 2.1. So the answer here is going to be 2.1%. It's better you go slow and pass the simple questions rather than rushing the simple questions and failing them. So that is the answer to that part. Use your answers in C Roman 1 and C Roman 2 to determine the absolute uncertainty in the calculated value of A. So we know the percentage in A is 2.1%. So the absolute in A is going to be 2.1 divided by 100 times the value of A. And the value of A that we got up there is 0.97. So I'll simply say times 0.97. So I'll check with my calculator. 2.1 divided by 100 times 0.97, which gives me 0.02 to one significant figure. Or you can write many, but at one significant figure, this is 0.02. Absolute uncertainties are good enough to one significant figure. So that is number one. That is the end of number one. Number one is always very easy. Number two. A motor uses a wire to raise a block as illustrated in the figure down there. So the base of the block takes a time of 0.49 seconds to move vertically upwards from level X to level Y. So the time to move from level X to level Y is 0.49 seconds at a constant speed of 0.64. Since the speed is constant, we can even tell the distance between X and Y. During this time, the wire has a strain of 0.001, so strain is 0.001. Normally we use epsilon for strain. The wire is made of Young modulus. We normally use capital E for Young modulus and has a uniform cross-sectional area. The block has a weight of 1.4 times 10 power 4 newtons. Assume that the weight of the wire is negligible. Calculate. The first one, they want us to calculate the cross-sectional area. So they gave us strain and Young modulus. And we know that Young modulus is equal to the stress. Stress is normally represented by sigma over strain, which is epsilon. And we also know that stress is force over area. So this is going to be the same as force over area for stress. Then because I don't want to bring in extension, I'll just say times, I'll put times epsilon in the denominator. So I want the cross-sectional area. So making the area the subject, I will say that area is going to be equal to the force, which is F, divided by, and the Young modulus goes in the denominator, so this will be E times epsilon. So I will substitute. The force is going to be the weight, which is going to be 1.4 times 10 power 4 newtons. Divide by, because the speed was constant, the tension upwards was equal to the weight. Because the speed was constant, the tension here is equal to the weight downwards. That's why I'm using 1.4 times 10 power 4 as the tension in the wire. Divide by Young modulus, which is 2.2 times 10 power 11, then times the strain, which is 0.0012. So 1.4 exponent 4 divided by 0.0012 times 2.2 exponent 11. So this is giving me an area of 0.0000, so which is 5.3. So the area is going to be 5.3 times 10 power 1, 2, 3, 4, 5, power negative 5 meters squared. So the answer is 5.3 times 10 power negative 5 meters squared. The increase in gravitational potential energy of the block for the movement of its base from X to Y. Increase. We want to calculate the increase in gravitational potential energy. So remember, the change in gravitational potential energy is equal to mg times change in height. But of course, mg is the weight, so I'll just simply say this is equal to the weight times change in the height h. But what is the height h, or what is the change in the height h? They gave us speed, which was constant at the time. So the change in the height h is going to be the speed. They gave us the speed, I guess. The speed was 0.64 and the time was 0.4. So in other words, we are saying distance is equal to speed times time. Because the speed is constant, when the speed is constant, we can say distance is equal to speed times time. So this is going to be the speed was 0.64. As long as the speed is constant, then the time given there was 0.49. Therefore, let's find the change in gravitational potential energy, which is going to be the weight, that is 1.4 times 10 power 4, then times m times g is the weight, so times change in height, which is 0.64 times 0.49. So I can check this with my calculator. So I have 1.4 exponent 4 times 0.64 times 0.49. Because these are all in SI units, I don't need to change anything. So this is giving me 4,390, or approximately 4.4 times 10 power 3. So this will be 4.4 times 10 power 3 joules. Okay. The motor has an efficiency of 56%. Calculate the input power to the motor as the base of the block moves from X to Y. Input power. We have seen the change. We have seen the increase in gravitational potential energy as 4.4 times 10 power 3. That is the increase in gravitational potential energy. But the motor has an efficiency of 56%. Okay. So we know that efficiency is going to be power input over power output. Efficiency is going to be equal to power output divided by power input. I will not include times 100 because I'm going to change this to 0.56. So efficiency is equal to power output over power input, or the useful output power over the input power. So we want to find the input power. The efficiency is 0.56. We want to find the input power. So we can begin by finding the output power. So output power, we know that power is equal to force times velocity. The velocity is constant. So the force is going to be the weight, which is going to be 1.4 times 10 power 4. The velocity is 0.64. So that is the useful output power. So the efficiency, which is 0.56, should be equal to 1.4 times 10 power 4. then times 0.64 divided by the power input. So input power, therefore, input power is going to be equal to, I'm just going to make input power the subject in my formula, my substitution. So I'll simply say 1.4 exponent 4 times 0.64, and I divide this by 0.56, which is 16,000. So this is 16,000. Or you can write 1.6 times 10 power 4 watts. Alternatively, you could find power from, we have the increase in potential energy. You could find the power from energy over time. Alternatively, I could find the power output as energy output, or the increase in gravitational potential energy over time, which we have got as 4.4 times 10 power, is it 4.4 times 10 power 3, divided by the time, which is 0.49. This is just an alternative. You could find the output power from the increase in gravitational potential energy over the time, because power is energy over time. That is 4.4 exponent 3 that we got above, divided by the time, which is 0.49. That is the output power. If I want input, so I will divide that by the efficiency, divided by 0.56. So it gives us approximately the same answer, 1.6 times 10 power 4 watts. The base of the block now has a uniform deceleration of magnitude 1.3 meters per second squared from level Y until the base of the block stops at level Z. Calculate. It now has a uniform deceleration. Let me take you back here. The base of the block now has a uniform deceleration. Remember, the system is moving upwards. If it has a uniform deceleration, the tension is upwards, the weight is downwards. If it has a uniform deceleration, it means the weight is greater than the tension. Therefore, the resultant force, which is given by mass times acceleration, will be equal to the weight downwards minus the tension upwards. Because that it now has a uniform deceleration, it means the weight is greater than the tension. That's why it is decelerating. Therefore, the mass, we can find the mass first. The mass is going to be got from weight divided by acceleration due to gravity. The weight was given as 1.4 times 10 power negative times 10 power 4 divided by g, which is 9.81. So it means I'll just substitute here. The mass will be 1.4 times 10 power 4 divided by 9.81, then times the acceleration, which is 1.3, should be equal to the weight, which is 1.4 times 10 power 4 minus the tension. So I want to make the tension the subject. So making tension the subject, tension is going to be equal to 1.4 times 10 power 4 minus 1.4 times 10 power 4 times 1.3 divided by 9.81. So here I'll just press my calculator. I'll start with this one here. So I have 1.4 exponent 4 times 1.3 divided by 9.81, which gives me that. So then I will say 1.4 exponent 4 minus the answer which I got. And this is giving me 1.2 times 10 power 1, 2, 3, 4. So it is 1.2 times 10 power 4. 1.2 times 10 power 4. Now you are seeing me writing these answers to two significant figures, but please avoid writing any answer which is not exact to less than two significant figures. As long as the answer is not exact, do not write it to less than two significant figures. Okay. The base of the block is at level x, y, and z at times tx, ty, and tz respectively. On the figure, sketch a graph to show the variation with the time t of the distance d of the base of the block from level x. Numerical values of d and t are not required. Number one, I want you to note that acceleration is constant, it is g. The base of the block is at levels x, y, and z at times tx, ty, and tz respectively. On the figure, sketch a graph to show the variation with the time t of the distance d of the base of the block from level x. Numerical values of d and t are not required. So let's first go back to the diagram here. They said the base of the block now has a uniform deceleration of magnitude 1.3. There's a uniform deceleration, meaning the speed decreases from level y until the base of the block stops at level z. So at z, speed is going to be 0. Okay. So going back here, between x and y, the speed was constant, so the distance increased from say 0 at x up to we calculated h, I think it was 0.64, but they said numerical values are not required. So here, because the speed was constant, I'll draw a sketch here of distance against time. For the first part between x and z, because the speed was constant, then the distance was increasing uniformly. Then here it is, let's say this was x, and let's say this is at y. So here the speed was, the distance was increasing uniformly because the speed was constant. And then there was a deceleration of 1.3 meters per second. So it means now the change, there will be an upward slope, an upward sloping curve with a decreasing gradient. So that means after y, from ty to tz, if we have tz somewhere here, this is ty, tz. Now this curve will have a decreasing gradient, meaning that the speed is decreasing because there is a deceleration there. Therefore, of course, at t, they told us at t equals to z, the velocity is 0, I think. It comes to rest. It comes to a stop at t equals to z. Where is that? Acceleration. Okay. There's a uniform deceleration of magnitude 1.3 from level y until the base of the block stops at level z. So at level z, the graph should now become perfectly horizontal. Therefore, since numerical values are not required, I'll just draw this graph. Where is my ruler? Okay, so it is a straight line between tx up to ty. It is going to be a straight line between tx up to ty. I'll use up to this point here. Let me use up to this point. It is going to be a straight line. That part is a straight line because the speed was uniform or constant. Then after ty, did I go beyond ty? Yes, ty is here. After ty, let me use a thicker line. After ty, now there was a deceleration, so the gradient should decrease. And at t equals to z, the velocity, it came to rest. So at z, the graph should be perfectly a horizontal line. Therefore, I'll take my graph like this. And at t equals to z, it is going to be a perfect horizontal line. Okay, so decrease starts from around here, or the straight line stops here, and now the curve starts of decreasing gradient, which becomes a perfect horizontal line at t equals to z. So this part is a straight line. So your graph should be somehow like that. With a pencil on a printed paper, you can draw something better than mine. So that is the graph. Note that from Tx to Ty, it is a straight line, which goes from Tx up to from Tx and 0, and then it stops at Ty because this the constant speed stops at Ty. Then now it goes, the gradient decreases because of the deceleration of 1.3. And at t equals to z, the line should be perfectly horizontal because at t equals to z, the gradient is supposed to be 0 since the body comes to rest. So the speed is going to be 0. Okay, that marks the end of question number 2. Question number 3. Question number 3. A uniform beam AB is attached by a hinge to a wall at end A, as shown in that figure. The beam has length of 0.5 meters and weight W. It is uniform. So since it is uniform, this weight is at the midpoint. So if the distance from A to B is 0.5, it means the midpoint is 0.5 divided by 2, which is 0.25. Therefore, this distance here must be 0.25. Mark that very well. A uniform body has its center, its weight acting at its center, or at its midpoint. Okay. Then a block of weight 12 newtons rests on the beam at a distance of 0.15 meters from end B. The beam is held horizontal and in equilibrium by a string attached between end B and a fixed point C. The string has tension 17 newtons and is at an angle 50 to the horizontal. Now note, coming back here, the tension here has two components. It has a component in the horizontal, which if you are good at resolving, this component is going to be 17 cos of 50. It also has a component in the vertical, which is going to be 17 sine of 50 when you resolve. Okay, state two conditions for an object to be in equilibrium. There are two simple conditions for an object to be in equilibrium. Number one, the resultant force in any direction is 0. Resultant, we saw this in force, density, and pressure. Resultant force in any direction is 0. Resultant force in any direction should be 0. Number two, the net resultant moment or torque about any point is 0. Resultant torque or resultant moment, resultant torque, resultant torque or moment about any point should be 0. So those are the conditions for an object to be in equilibrium. Show that the vertical component of the tension in the string is 13. I think that is very easy. We have finished resolving the vertical. Resolving 17 to the vertical, we have seen it is 17 sine of 50. So we have 17 sine of 50, which is going to be equal to 17 sine 50, that is 13.022, which is approximately 13 newtons as required. By taking moments about end A, calculate the weight W of the beam. How many marks? Just 2. So we are going to take moments about end A. Now that we have the vertical, the component of the tension in the vertical, we don't need the component in the horizontal because it will not have any moment. Reason, if I extend the line of action of the horizontal component to go through end A, so it has no moment. I will only consider 17 sine 50, which is equal to 13. And its perpendicular distance will be 0.35 plus 0.15, and this would cause an anticlockwise moment. The weight is going to cause a clockwise moment. 12 newtons is going to cause a clockwise moment. Therefore, taking moments about A, the weight W times its perpendicular distance, which is 0.25, will cause a clockwise moment, plus 12 newtons times its perpendicular distance, which is 0.35, will cause a clockwise moment, should be equal to uh, 13 newtons, which is anti-clockwise, 13 newtons, that is the component of 17 in the vertical. So it will be 13 newtons times the perpendicular distance of 13, which is 0.5. 0.5. So that is the equation we are going to solve. So I will transfer it at the bottom there in the space provided. So we have had that we shall have the weight W times its perpendicular distance, which is 0.25, plus the 12 Newton force times its perpendicular distance, which is 0.35. That is the sum of clockwise moments, should be equal to the sum of anticlockwise moments, which is 13 times the perpendicular distance, which is 0.5. So I'll just press my calculator. From the right hand side, I have 13 times 0.5, then minus 12 times 0.35, then divide by 0.25. So that gives me 9.2. So W is equal to 9.2 newtons. So W is equal to 9.2 newtons. I'll just write here 9.2 newtons. Okay. Calculate the magnitude of the vertical component of the force exerted on the beam by the hinge. So let's go back to the hinge. Now remember the weight is 9.2. So this is 9.2. Now note that the first condition was saying the resultant force in any direction is 0. But in the vertical direction downwards, we have 9.2 plus 12, which gives us 9.2 plus 12, which gives us 21.2. 21.2. So in the vertical direction downwards, we have 21.2. Yet upwards, we only had 13 newtons upwards. Therefore, there must be a force here, the force at A, which combines with 13 newtons to balance with the forces acting downwards. Therefore, in our solution, we shall say the force at A, which is acting downwards, the vertical component of the force exerted on the beam by the hinge, which I'm calling FA, which is acting upwards, plus the force, the component of the weight of the tension upwards, which is 13, should be equal to the total forces downwards, which was the weight 9.2 plus 12. So it means FA is going to be equal to 21.2 minus 13, which gives us 8.2. So this is 8.2 newtons. So our answer here is 8.2. The block is now moved closer to end A of the beam. Assume that the beam remains horizontal. State whether this change will increase, decrease, or have no effect on the horizontal component of the force exerted on the beam by the hinge. The block is now moved closer to end A of the beam. Assume that the beam remains horizontal. The beam remains horizontal. State whether this change will increase, decrease, or have no effect. Increase, decrease, or have no effect on the horizontal component of the force exerted on the beam by the hinge. The horizontal component of the force exerted by the hinge on the beam. Okay, so we have moved the block. We have moved the block closer to A. We have moved the block closer to A. If we move the block closer to A, the tension here is most likely going to reduce. The tension in the string reduces as we move the block towards end A. And if the tension reduces, the horizontal component of the force on the hinge on the beam is going to be 17 cos 50. It's going to be the tension cos of 50, which is going to be also reduced since the tension has reduced. Therefore, we can conclude that actually the force does what? Decreases. The change, or the same state whether this change will increase, decrease, or have no effect on the horizontal component of the force exerted on the beam by the hinge. So if we move the block closer to end A, it means we have even reduced the tension in the string. Therefore, we have seen that this decreases, so it will decrease. Okay, so the horizontal component of the force exerted on the beam by the hinge decreases. Okay, that's the end of question number 3. Let's move to question number 4. The two blocks slide directed towards each other along a frictionless horizontal surface as shown in the figure. The blocks collide and then move as shown. So here they are moving towards each other, then they collide. So we shall first of all assign velocities to the right positive and maybe to the left negative. So I'll say this is positive, negative, negative, negative. I'll call this velocity v. Block X initially moves to the right with the momentum 0.37. Block Y initially moves to the left with the momentum 0.65. After the blocks collide, block X moves to the left back along its original path, while with a momentum of 0.13. Block Y also moves to the left after the collision. Block X has an initial kinetic energy of 0.3 joules, calculate the mass. Okay, they have given us the initial kinetic energy. You and me know that kinetic energy is equal to a half mv squared. So they have given us kinetic energy. We don't have the mass. We don't have the speed, but we also know that momentum is equal to mass times velocity. So if your mathematics is poor, you can first use momentum and you make v the subject. But for us who are good at mathematics, like me and you, we shall say, okay, v is equal to p over m. Then I'll go and substitute for v there. So it means kinetic energy is going to be equal to a half times m times, because v is squared, this will be momentum squared over mass squared, and the square cancels. So I remain with kinetic energy, which is given as 0.30, is going to be equal to 0.5, a half here, times the momentum. You are looking at block X initially. Block X momentum is 0.37, so I'll say times 0.37, but is squared, divided by m. I'll just press my calculator to find m. So I will have 0.5, that is a half, times 0.37, but squared. Then I divide this by 0.3. Okay, so it means the mass is going to be 0.23. So m is 0.228, and so on and so forth. So I'll just say 0.23. So the mass is 0.23. These three marks are too much. There is nothing much serious here. Determine the magnitude of the momentum of block Y after collision. Remember, conservation of momentum, total momentum before collision should be equal to total momentum after collision. For an interacting system, for an isolated system of interacting bodies, total momentum is always constant. So total momentum before collision, remember we said we gave these values, these quantities signs, because momentum is a vector. It means the velocity is also a vector. So let me call this one p instead of v, because we don't need the velocity. So total momentum before collision, momentum to the right positive, momentum to the left negative. So total momentum before collision is going to be 0.37 plus negative 0.65. It should be equal to total momentum after collision. They are all to the right, so we have negative. The first one is 0.13, so this is 0.13 plus. The other one is also negative, so I'll say plus negative p, or just minus p, because I've said momentum to the right, to the left is negative, so that is minus p. So just check with the calculator. I'll simply say 0.37 minus the 0.65, because this is minus, when it crosses it becomes plus 0.13. So this gives us a negative 0.15 equals to negative p. So P is strictly 0.15. Block X exerts an average force of 7.7 newtons on block Y during the collision. Calculate the time that the blocks are in contact with each other. So we know that force average net resultant force is equal to the rate of change of momentum. Change in momentum with the time t. They have told us the average force is 7.7. We know the change in momentum. Block X exerts an average force of 7.7 newtons on block Y during the collision. Calculate the time that the blocks are in contact with each other. So the force is 7.7. This is going to be equal to the change in momentum. The change in momentum after the collision, remember block X. Let's go back here. So block X has initial momentum 0.37 before collision, and after collision its momentum is 0.13. So the change in momentum is going to be 0.37 minus negative 0.13 because this one is in the opposite direction. So the change in momentum of block X, the change in momentum, I'm looking at block X. So this is going to be 0.37 minus negative 0.13 divided by the time taken. So this gives us t. Of course, this part becomes positive. So this is going to be 0.37 plus 0.13. Then I divide this by 7.7, which gives us 0.065. So time is 0.065 seconds. I have considered block X. I could also have considered block Y because by Newton's third law, the forces are equal but opposite. So block Y again, the force is equal but opposite is going to be equal to the rate of change of momentum. So I will say 7.7. This is another alternative, remember. 7.7 is equal to, for block Y, its initial momentum was, I think it was 0.65. 0.65 to the left, to the right-hand side. Sorry, 0.65 to the left-hand side. And its momentum after collision is 0.15. This momentum here is positive. That means it is not in the same direction as, okay, it is in the direction shown. It is also to the same side. So if I want the change, I may ignore the signs because they are in the same direction. So I can find the change in momentum by just subtracting 0.65 minus 0.15 because they're in the same direction. I can ignore the signs to find just the change. Divide by the time. So I'll just say time is going to be equal to 0.65 minus 0.15, then divide by 7.7, which gives us the same thing. So this gives us again the change in time as 0.065 seconds. So the answer is 0.065. Okay. I think that marks the end of that is what? Dynamics. That was dynamics. Yeah, it was very sweet and simple. A microphone and cathode ray oscilloscope are used now. This is waves, I think. Are used to analyze the sound wave of frequency 500 Hertz. The trace that is displayed on the screen of the CRO is shown in the figure here. So you see 5 small squares are represented by 1 centimeter on both the vertical and the horizontal. Determine the time-based setting. Determine the time-based setting. So my students always prefer to say that, okay, the period or the frequency is equal to 1 over the period. Frequency is 1 over the period, and that means this is going to be 1 over, or that means the period is going to be 1 over the frequency, which is going to be 1 over 5,000. Now remember, hertz is per second, so this is per second, which makes this to be in seconds. So I will say frequency period is equal to 1 over 5,000 seconds. But period is going to be equal to the length representing one cycle times the time-based setting. Length representing one cycle in centimeters times the time-based setting. So let's go to the trace. So we have between this point here and this point, that is one cycle, or from here up to here is one cycle. So this is 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters. So the length representing one cycle is 4 centimeters, and we want the answer in seconds per centimeter. So I'll simply say that 1 over 5,000 in seconds is equal to 4 centimeters times x. I want x. So x is going to be equal to 1 over 5,000 times 4 centimeters. Remember, this is in seconds. So it is going to be seconds over centimeters, which is going to be seconds per centimeter. So this is going to be equal to 1 divided by 5,000 times 4. So the time-based setting is going to be 5.0 times 10 power 5 times 10 power negative 5. So this is 5.0 times 10 power negative 5 seconds per centimeter. That is the time-based setting. The intensity of sound detected by the microphone is now increased from its initial value of I to a new value of 3I. The frequency of sound is unchanged, so frequency is remaining the same. That means the graphs are going to pass through the same points in the horizontal line drawn there. Assume that the amplitude of the trace on the CRO is proportional to the amplitude of the sound wave. Amplitude of the trace is proportional to the amplitude of the sound wave. Sketch the new trace shown on the screen. So the intensity of the sound detected by the microphone is now increased from its initial value is I and its new value is 3I. So I'm going back to this part here. We know that intensity is directly proportional to amplitude squared. Intensity is directly proportional to amplitude squared. When the intensity was I, the amplitude was represented by 1, 2, 3, 4, 5, that is 1 centimeter. So the amplitude was 1. I'll just say 1 centimeter squared. Now let's say when the intensity is 3I, this is going to be equal to a constant times the new amplitude, which I say A2, but it is also squared. So I divide these two equations. I'll say 3I divided by I is equal to K A2 squared divided by K times 1 squared. So I've not changed the units because the answer will still be in centimeters. So K has cancelled. So I cross multiply. It means amplitude 2 is going to be equal to the square root of 3. What is the square root of 3? So root 3 is equal to 1.7, approximately 1.7. But remember, 1 centimeter is represented by 5 boxes. Let me see. One small square is going to be 1 over 5. Remember, this is in centimeters. One small square is 1 over 5 centimeters. So how many small squares? Oh, this is the same as 0. I think 2. Yes, 1 divided by 5, 0.2 centimeters. One small square represents 0.2 centimeters. How many small squares do I need for 1.7 centimeters? So I'll just say that answer divided by 0.2. So I'll need 5, I'll need approximately 8, approximately 8.5 or 8 or approximately 9 small squares. Since the frequency has not changed, I'll just draw a new trace almost with the same period as this one. The new trace must have an amplitude which is greater than the first one. The amplitude for the first one was 1 centimeter. So this should be approximately 1.7 centimeters, which is going to be about 8.5 or approximately 9 small squares. So I will add 1, 2, 3. So it is around here. So the new trace will go like this. Let me increase the thickness. I don't want to make it exactly 9 squares because it will be greater. So this is 1, 2, 3 around here. You can draw a better one. 1, 2, 3. I'm adding 3 small squares there because they're already 5 and I want 8.9.6 small squares, which is approximately 9 small squares from the horizontal line which is dotted. So this will also be here. So with the pencil you can draw a better line, but I think I've given you a clue on how it should look like. Its amplitude should be 1.7 centimeters because intensity was directly proportional to amplitude squared. Okay, so that was the graph. The graph was that. The graphs are meeting at these points because the period is the same or the frequency is the same. Okay. An arrangement for demonstrating interference using light is shown here. This is a double slit. And if you have gone through videos of waves and you have also watched multiple choice questions of waves, I think questions of double slit are the easiest in waves. Light from laser, wavelength 630 nanometers, and then the slit separation is given as 3.6 times 10 power negative 4 meters. The distance between the slits and the screen is d. The wavelength of the light from the laser is 630. The light is incident normally on the double slit. The separation of the two slits is 3.6 times 10 power negative 4. The perpendicular distance between the double slit and the screen is d. Coherent light waves from the slits form an interference pattern of bright and dark fringes on the screen. Coherent, they maintain a constant phase difference. The distance between the centers of two adjacent bright fringes, so that is labeled as small x, is that the central bright fringe is formed at P. So the central bright fringe is formed at P where light travels the same distance from both slits. Okay. Explain why a bright fringe is produced by waves meeting at P. Of course, we have seen here the path difference from the slits to P is 0 because light travels the same distance from each of the slits. At P, P is the center, light from this slit will travel the same distance as light from that slit. That means the path difference is 0. So constructive interference occurs. Therefore, we can say the path difference from the slits, from both slits, from both slits to P is 0. Or in other words, if the path difference is 0, you could also say the phase difference or phase difference or phase difference or the phase difference between the waves at P when they meet at P is 0. And if the phase difference when they meet at P is 0, it means so constructive interference occurs. So constructive interference occurs. So constructive interference occurs at P. That's why the bright fringe is formed. The bright fringes are formed when constructive interference has occurred. Because the light travels the same distance, the path difference from both slits to point P is 0, or the phase difference between the waves at P is 0. So constructive interference occurs at P, resulting into a bright fringe. Then calculate D. You and me know the Young's double slit formula, that is lambda is equal to AX divided by D. So in making D the subject, D is going to be AX divided by wavelength. This means A is the slit separation was 3.6 times 10 power negative 4. Then the fringe separation, which was 4.0 times 10 power negative 3. These are in SI units, divided by the wavelength, which is 630, but was in nanometers, so I'll say times 10 power negative 9. 3.6 exponent negative 4 times 4 exponent negative 3 divided by 630 exponent negative 9. So this is giving us 2.29. So D is equal to 2.29 in meters. Yes, 2.29 in meters, or 2.3 to two significant figures. 2.3 meters to two significant figures. Okay, the wavelength lambda of light in B is now varied. This causes a variation in distance x between the centers of two adjacent bright fringes on the screen. The distance d and the separation of the two slits are unchanged. Okay. On the figure, sketch a graph to show the variation of x with the wavelength lambda. With the wavelength lambda from lambda equals to 400 to lambda equals to 700 nanometers. Numerical values of x are not required. So as the wavelength increases, let me just go back to the formula. Lambda is equal to ax divided by d, and we want x against lambda. I make x the subject, so x is going to be equal to d over a times lambda. So they have told us d and a are remaining constant. You notice that if d and a are constants, x is directly proportional to the wavelength. So this means of course this graph cannot start from x equals to 0, because the wavelength is not also starting from 0. Therefore, the wavelength is we are starting with 400. Therefore, our x cannot start from 0. So our graph will not start from 0. At 400, there is a value of x, but then x is directly proportional to lambda. So this is going to be a straight line with increasing. The gradient is constant, so this is going to be a straight line. As lambda increases, x also increases. So this is a straight line with a constant gradient. So this is going to be a straight line. Why isn't it starting from 0 and 400? Because when the wavelength is 400, x is not 0. So it cannot start from 0, 400, or 400 and 0. So it should be a line with a non-zero value at x at wavelength equals to 400. So that is going to be the graph. Okay. Isn't waves ending there? Okay, waves have ended. You notice that waves have been very easy. This year, the question paper was very easy. I don't know, maybe because I'm the teacher. Define the potential difference across a component. Define PD. We can define PD in terms of energy, that is V is equal to energy per unit charge. Which energy is this? Energy is being transformed from electrical to other forms such as thermal per unit charge. So PD is going to be energy transferred. Energy transferred from electrical to other forms such as heat. I will put heat in brackets, per unit charge. So that is PD. If it was EMF, it would still be energy transferred from chemical to electrical per unit charge. But this is now PD. Okay. The variation with the potential difference V of the current I in a semiconductor diode is shown in the figure. Okay, this is also, if you're very observant, is looking like a past paper question. that we have solved. Use the figure to describe qualitatively. Use the figure to describe qualitatively means you don't need to quote any value. Use the figure to describe qualitatively the resistance of the diode in the range V equals to 0 to V equals to 0.25. V equals to 0.25, I think 1, 2, 3, 4, 5. 0.25 might be there. So you notice that from I is equal to V over R, between 0 to 0.25, it's like there is no current. When I is equal to 0, it means the resistance must be infinite. So the resistance is infinity at between 0 and 0.25. So you can simply say the resistance is infinite or very high, but more probably it is infinite. So resistance is infinite, or resistance is infinity, depending on what you want to state. So resistance is infinity because there is no current flowing. So it is infinity or it is infinite. Then use the figure to describe qualitatively the variation, if any, in the resistance of the diode as V changes from 0.75 to 1 volt. 0.75, I think 0.75 is 1, 2, 3, 4, 5. This is 0.75 to 1 volt. I want you to notice that this is a straight line. This is a straight line, but if we use the expression V is equal to, if we use the expression I is equal to V over R, I don't want to say that the gradient is constant because it is a straight line, but I want to just use the formula V or R is equal to V over I. We notice that as V increases, I is increasing. That means the resistance there is actually decreasing. As V increases, you even see that I increases more rapidly than V, so it means the resistance decreases. So I increases more rapidly. I increases more rapidly than V. So it means R increases. I mean, it means R decreases, not increases. R decreases. If more current flows through the circuit, it means R has decreased. So we can say uh, resistance decreases. Resistance decreases as V increases. We have seen the graph is showing that I increases more rapidly than V, or as V increases, I increases more rapidly, so the resistance is decreasing. So the answer is resistance decreases. Resistance decreases as V increases. Okay. A battery of EMF 12 volts and negligible internal resistance is connected to a uniform resistance wire XY. A fixed resistor and a variable resistor as shown in the figure. So this is a potentiometer. The fixed resistor has resistance 5 ohms. The current in the battery is 2.7 amperes and the current in the fixed resistor is 1.5. So current in the battery is 2.7 and the current in the fixed resistor is 1.5 amperes. Calculate the current in the resistance wire. Of course, this one is easy. We shall use Kirchhoff's first law here. The current divides. So this current in the wire plus 1.5 should give us 2.7. So I plus 1.5 should give us 2.7 according to Kirchhoff's first law. The sum of currents entering a junction should be equal to the sum of currents leaving the junction. So I will say 2.7 minus 1.5, which is 1.2. So that current is 1.2 amperes. Determine the resistance of the variable resistor. Determine the resistance of the variable resistor. First of all, the PD across the wire is going to be 12 volts, which also means that the PD across this side is also going to be 12. But I can find the PD across this 5 ohm resistor, which will be A PD here is going to be the current times the resistance, which is going to be 1.5 times 5. The PD there is 1.5 times 5, which is 7.5. So the PD here is 7.5 volts. But these are in series, that means the current flowing is the same. And I can find the PD here, which is going to be 12. The PD here is going to be 12 minus 7.5. So the PD here is going to be 12 minus 7.5, which is going to be 12 minus the answer, which is going to be 4.5 volts. So the PD across the fixed resistor is 4.5. But remember, the current is the same. The current is the same. So if the current is the same, then it means the resistance is going to be V over I, which will be 4.5 divided by I, which is 1.5. So that means this will be 4.5 divided by 1.5, which gives us 3 ohms. So that is 3 ohms. I don't know how easy this could be, but anyway, let's solve this. Therefore, we can say the PD across all of them is going to be 12. The PD across all of them is going to be 12. So 12 is going to be the PD across 5 ohms plus the PD across the fixed resistor. I'm going to call it R. I mean the variable resistor R. Then, so it means 12 is equal to the PD across the 5 ohms, which is going to be current. Remember, V is equal to I times R. So PD across 5 ohms will be the current, which is 1.5, times the resistance, which is 5 ohms, or 5.0, plus the PD across the fixed resistor, where the current through it is also 1.5, times its resistance, which I'm going to simply call R. Therefore, this means I'm having 12 minus, we said 1.5 times 5 was 7.5, which gave us the PD across the variable resistor. So I will divide this by 1.5. This is going to be equal to R. So this is automatically giving us R as 3.0 ohms. So the answer here is going to be 3.0. Okay, so that is the resistance of the variable resistor. Okay. Wire X has length 2 meters. Point Z on the wire is a distance 1.6 meters from point X. The fixed resistor is connected to the variable resistor at point W. Determine the potential difference between points W and Z. So let's go back to the diagram. We want the potential difference between W and Z. Now we know the potential at this point because we know that the current here is 1 point. What was the current there? The current here is 1.2. That length is 1.6. The current is 1.2. What is the resistance of this wire? So the wire has a length of 2 meters. Point Z on the wire is a distance 1.6 meters from point X. The fixed resistor is connected to the variable resistor at point W. Okay, determine the potential difference between points W and Z. So we are going to find the PD between W and Z. So first of all, the PD across the wire XY is 12 volts. I'm going to get the PD per meter, PD per unit length. First, PD per unit length, PD per unit length across the wire is going to be equal to the PD across the wire is 12 volts divided by the length of the wire is 2. So this is the PD per unit length. This is going to be in volts per meter. That's the PD per unit length. That means the PD across length X, that is X what? XZ, which is 1.6 meters. PD across XZ is going to be the PD per meter, which is 12 over 2 times 1.6. That means the PD across that length is going to be 12 divided by 2 times 1.6. That PD is 9.6 volts. So the PD across that part is 9.6 volts, and we know the PD across the 5 ohms, or PD across the PD across XW is 7.5 volts. We have calculated it here. Now we have seen the PD across XZ as 9.6 volts. So that one is very easy. So PD across XW was 7.5 volts. That means PD between W and Z is going to be 9.6 minus 7.5, which gives us 9.6 minus 7.5, that gives us a 2.1. So the PD across W and Z is 2.1 volts. The resistance of the variable resistor is now increased. That means the PD across the variable resistor must increase. By considering the currents in every part of the circuit, state and explain whether the total power produced by the battery decreases, increases, or stays the same. By considering the currents in every part of the circuit, state and explain whether the total power produced by the battery decreases, increases, or stays the same. So remember, the variable resistance is the one which is increased. So let's go back to the circuit because we can't answer this without going to the circuit. So the resistance here has been increased. What does that mean? If the resistance here has been increased, it means the current in this fixed in the fixed resistor here decreases, of course. The current in the fixed resistor or even the variable resistor decreases. So the current here is going to decrease. But the current in the resistance wire is not going to be changed. The current in the resistance wire is not going to be changed. Why? The PD across the resistance wire is going to remain 12 volts. That's number one. Number two, the resistance of the resistance wire XY has also not changed. So it means the current in it is still going to remain 1.2. But the current at the bottom is going to change. The current in the fixed resistor or in the variable resistor is going to be decreased because the resistance down here has been increased. So what has happened to the 2.7? Remember, total current, if the total current is here, the total current entering here is the sum of this current and the other current. The current here, the current down here has reduced. Let me call this one I2. This was I1. Let me call this one I1. Let this be I. I is equal to I1 plus I2. And I've said I1 has not changed. Why? The resistance of the wire XY has remained the same. The PD across the wire XY is still 12. So it means the current is still 1.2. It has not changed. But then the current here down, the resistance down here has increased, which means the current down here has decreased. So I2 has decreased. And if I2 has decreased, yet I is equal to I1 plus I2, it means I has also decreased. So it means the current in the battery has decreased. And if the current in the battery has decreased, the question is asking us to talk about the power in the battery. By considering the currents in every part of the circuit, state and explain whether the total power produced by the battery decreases, increases, or stays the same. Since the current through the battery has decreased, it means the power has decreased. Therefore, we can simply say that the current at the lower branch, which is where we have the fixed resistor, the current in the fixed resistor, and the variable resistor, because it is the same. The current in the fixed resistor, or let me just say O, because the current is the same. The current in the fixed resistor or variable resistor the current in the fixed resistor or variable resistor decreases. Why? This is just for explanation. Why? Because total resistance down there, resistance along that path increases. Resistance there, resistance resistance there, let me just say resistance there has increased. Resistance there increases, but PD did not change. PD remained 12. This is just for explanation. The resistance down there in the lower part of the circuit increased, but the PD remained 12. That means the current must have decreased. And the current in the resistance wire did not change. The current in the resistance wire, did not is unchanged or is unchanged. Why is the current in the resistance wire unchanged? The resistance of wire XY did not change, RXY did not change. And the PD remained what? Remained 12. The PD across XY still remained 12. That means the current does not change. However, I want to take you back. If the total current I from the batteries, the total current from the batteries I, part of it goes to the wire XY, and part of it goes to the lower part. It goes through the variable resistor. Let me call it I into the variable resistor R, or in the resistors down there. But we have said the current in the resistors down have reduced, and current in XY has not changed. That means I has reduced because it depends on the sum. So it means the current in the battery, decreases. And if current in the battery decreases, it means for the same EMF, the power decreases. Current in the battery decreases. So for the same EMF, the power decreases. Why? The power produced in the battery is going to be I times the EMF. The current has decreased, the EMF has remained the same, so the power decreases. Okay, and that marks the end of electricity. And finally, I think it is particle physics, atomic physics and particle physics. This one is always very easy, so you don't need to waste a whole night revising atomic physics. Nuclei X and Y are different isotopes of the same element. Remember, isotopes are nuclei with the same proton number but different nucleon number. Nucleus X is unstable and emits a beta plus particle to form Z. By comparing the number of protons in each nucleus, state and explain whether the charge of nucleus X is less than, the same as, or greater than the charge of nucleus Y. First of all, they said they are isotopes, so they have the same number of protons. And the charge of the particle depends on the number of protons, so it means they have the same charge. So we can say X has the same number of protons as Y. X has same number of protons, because they are isotopes, same number of protons as Y. And so the charge of X, and so the charge of X is the same as the charge of Y. Okay, so they have, because they are isotopes, they have the same proton number. Then nucleus X is unstable and emits a beta plus to form nucleus Z. So let's see, nucleus X is forming nucleus Z by emission of beta plus. Beta plus is going to be 0, 1. So Z has proton number. The proton number of Z must be, okay, the proton number of Z, this is, okay, Z is normally what we use for proton number, so this one does not change. A has not changed. Let me use Y here. So this will be Y minus 1. So the proton number is reduced by 1. So by comparing the number of protons in each nucleus, state and explain whether the charge of nucleus X is less than, the same as or greater than the charge of, this time we are looking at nucleus X. So we now have that nucleus Z has one proton number less than nucleus Y, or X has one more proton than Z because of this part here. So you can say X has one more proton than Z. X has one more proton than Z, so it means because remember charge depends on the proton number, it means X will have a greater charge. So X has a greater charge than Z. So X has a greater charge than Z. And lastly, hadrons can be divided into two groups, classes P and Q. Group P is a baryon. State the name of group Q. So hadrons are both baryons and mesons, so group Q must be mesons. Remember, baryons, all hadrons are made up of quarks. Baryons are made up of 3 quarks. Mesons are made up of a quark plus an antiquark, as we discussed this in atomic physics. Describe in general terms the quark structure of hadrons that belong to group Q. So group Q, that is a quark and an antiquark. So this is one quark, and one antiquark. So mesons have one quark and one antiquark. Baryons have 3 quarks. Baryons are made up of 3 quarks. Then particles with antiquarks only can be called antibaryons if they are 3, or we can call them antiparticles. But here for a meson which has one quark and one antiquark, for example, up and anti-up, that is a meson, which could be a pi meson. Therefore, such particles are called mesons if they have one quark and one antiquark. I think that marks the end of February-March 2023, paper 2. See you in another paper. All the best. I hope you learned something from this. And do not hesitate to download the question paper and try to practice. I think if you have been watching the solved past paper questions in all topics, this paper was very, very, very easy. I'll stop there. Bye bye.